Okay, I think got a good number of attendees now. So my name is James Richings. I'm managing this ARCHER2 webinar today. The topic of this week's session is Python overhead reducing the burden. It will be presented by Michael Bareford, a member of the ARCHER2 CSE team. Please ask any questions in the chat as we go, and we'll collect them for the session at the after the session. We'll make time for some discussions. But I will hand over to Michael now.
Okay. Okay, thank you for the introduction, James. So I think I'll start just by explaining the title, Python Overhead, Reducing the Burden. So in the last few years, Python has become increasingly popular on the HPC machines that we support, namely Cirrus and ARCHER2. And I think that's because, having used Python myself, I know how easy it is to get started. Because of the abstractions that you have available, it's very easy to write your Python scripts such that you're using the terms which are used to describe the problem you're trying to solve. And the other things, the low-level things such as how your arrays and matrices are represented, are taken care of for you. However, this does cause a problem when you want to do parallel processing and you're using HPC machines, because that's time that you are paying for. And so there is a need for certain Python packages to be linked to the right libraries to do the parallel communications. Those libraries must be built for the underlying hardware. And so there was therefore a need to put together a set of Python modules that were in a central location, meaning that they will be accessible to all users. And then that reduces the burden, as the user doesn't need to know so much about the details of the underlying hardware. They can run their Python scripts and they'll be certain that they'll be able to run them in a parallel processing environment, and then they should run in a performant manner. Also reduces the burden for us, the people that support users on our HPC platforms, and we can easily roll out improvements to the centralized modules, and they would be automatically picked up by the users. So I'm just going to turn off my video so it doesn't distract too much. I should say that there's a chance that there may be some gunfire during my talk. I don't know if it's going to be picked up by the microphone on my headphones, but in Edinburgh, King Charles is continuing his coronation celebrations, and I understand there's going to be a 21-gun salute, so I don't know, hopefully that won't be picked up. But anyway, moving on, I have the obligatory reusing this material slide. I just skipped that. So I'm going to show examples or explain how you can set up a local Python environment within your the project area that you have under your own user account, and that local Python environment will then automatically include the Python packages that are provided by the centralized Python modules, and so you'll be using the right modules for the hardware. So I'm going to cover Cirrus and ARCHER2. Cirrus is just a slide that introduces the machine. So it's our tier 2 machine. It has Intel Xeon processors. It's about it has about 11,000 cores. It has CPU nodes and it has GPU nodes. The GPU nodes have 4 NVIDIA V100 GPUs each. The nodes are connected via InfiniBand Fabric, and there's a number of options for file storage. So on Cirrus, there are a number of modules, and we have Python modules, and we have 2 categories of Python modules. These are the ones installed in a central location, and they're written using the TCL command language. So the 2 categories are for the CPU nodes and another category for the GPU nodes. And when a module has a -GPU, that just indicates that it's meant to run on the GPU nodes and not the CPU nodes. The version number just follows the version of Python that's being used. So each of these Python modules will provide a number of Python packages allowing you to do parallel processing on the Cirrus compute. Now, if you were to run module help for these Python modules, you'll get some details that show you what's happening underneath. So each of these Python modules is in fact a mini-conda installation. So mini-conda is a lightweight Python distribution that allows you to put together the minimal set of Python packages needed for your requirements. It also includes a package manager called pip, which we recommend you use to then install the specific packages that you need in your local environment. It also includes conda, but we don't recommend you use conda, mainly because when you do a conda install, it will duplicate the centrally installed packages in your local environment. So this will take some time, and it will also eat into your disk space allocation that you have. So we recommend you use pip instead, and the instructions that I'll show later, we use pip. So here I'm just showing, again, for each of these Python modules, the corresponding mini-conda versions that exist, and you can see they're quite long. And so this is the reason why the module file itself just indicates the underlying Python version and whether or not it runs on the CPU or the GPU nodes. So as I said, each of these Python modules provides a suite of Python packages. And for the Python 3.9.13 module, I'm just showing you the list. We have Dask, we have packages for interactive Python and for serving Jupyter Lab, and MPI for Py, which is a crucial one, allowing you to do MPI comms within your Python scripts. And for an example, for a Python module for the GPU nodes on the right, we've got a similar set of packages, but also includes ones specifically for the NVIDIA GPUs, and that's the cupy, CUDA 11.6, and the pycuda modules. Now, some of these packages that are provided centrally have been built such they are linked to specific libraries, and in the case of Cirrus, these are the MPI library is OpenMPI, and that also includes the low-level UCX communications library. And then we also have other libraries specific to NVIDIA. So that just gives you an overview of the structure, how the Python modules are set up. So if you are wanting to create your local Python environment and you're on a logging node, the first thing you do is to choose the central Python module that you want to base your local environment on. And this is what the first command does that you can see here, the module load command. And then when you've done that, you've just got to go through a series of 4 commands to actually set up your local environment. The first of which is you're just setting an environment variable, which gives the location of your local environment. And when you've done that, you can then run Python, the Python interpreter. So you're going to call it with the virtual environment module, that's the VM. And then the system site packages option is just indicating that you wish to use the packages you wish to include in your local environment, the packages that are installed centrally. And then obviously you pass it the path for your local environment. When you've done that, there's an extra step. You need to run this extend VM activate script. And what that does is a simple bash script, which is provided centrally by the Python module. It's a simple bash script that just adds extra instructions into the activate script. And these instructions just make sure that the base Python module is loaded and unloaded whenever you activate and deactivate your local Python environment. And then finally, the last command to get you into a position where you're ready to install your own local packages is you basically sourcing your activate script. You're activating your local environment. So now you're ready to use Python -m pip to install your packages, and you can also install specific versions of a package if you require that. And then at the end, once you've finished, you just simply call deactivate to deactivate your local environment, which will unload any of the modules which you may have, and then you go back to your normal login prompt. And if at a later date you need to add more packages or change the packages that you have in your local environment, you can do that. You don't have to run through all of those commands that I've shown. When you go back into a new login session, you just need to source the activate script, and away you can go with your pip uninstall or your pip install commands, whatever you need to do. So once you've done that, this is kind of showing you where things are located. In the top box are the packages that you may have installed in your local environment, and there's some examples here. There's Metis, and then a package called PyFR. PyFR is a Python CFD code, so you might have a local environment like that. And then, so obviously, this is based on a centralized Python environment, so it'll also include the packages that are provided from a central location. And this is this Mount Luster Indy blah 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 Minicopter 3. That's the environment or the set of packages that corresponds to the Python 3.9.13 -GPU module. That's in red. So that just gives you an overview of where packages are coming from. And then you may need to do further customization for your local environment. You may want to specify other environment variables. You may want to load other modules. So the best place to do that is just in the activate script, which is held locally. So you'll have full access to that. And so you can add extra activation commands as indicated. And then also when you come to deactivate your environment, you'll add corresponding deactivation commands. So module unloads or Python or environment variable unsets, things like that. So finally, you've got your local environment set up, you're ready to go. It's very simple to run that on the compute nodes. The key thing really is to make sure that, obviously I didn't mention this, is that your local environment is on /work. And this is what this line does here, where I have my mouse pointer. I hope you can see that. So you're taking your home and then you're replacing the home part with work. So your local environment is on /work, meaning that it can be seen from the compute nodes. You source your local environment, all of the Python packages that you've installed locally, as well as the central ones should be available, and you're ready to run your Python script. And this script is, in this example, is running across 2 GPU nodes. I have 8 MPI ranks. So I mean, assuming it's, yeah, so each MPI rank is assigned a GPU, basically. So that's how to do it. There's just a link that you can go to the official Cirrus documentation, which just goes through what I've explained over the last few slides. And here's the first example I'm going to give, the first use case of a local Python environment using a centrally installed one on Cirrus. And this one uses the Python CFD code. CFD stands for Computational Fluid Dynamics. And this is about simulation Martian Aerodynamics on Cirrus. So what this user wanted to do, that they wanted to do a simulation of the airflow around an airfoil. I think that was going to be used, envisaged to be used as a helicopter blade. And so on Mars, the atmosphere is thinner. The speed of sound is about 3/4 that on Earth, and you have a lower Reynolds number between 1,000 and 10,000. And so they wanted to run this CFD code on the Cirrus GPU nodes, and I've just got, I've got the graphic on the left is showing the grid. Each of the segments in that grid is going to be collected and then partitioned, meaning it will be distributed over the various MPI tasks that are available, and that's what the Metis partitioner does. And then so on the right are some results. I think these are ISO surfaces of velocity, and they're showing the wake on the back of the airfoil. So when the user wanted to do this initially, they found that they had problems because when they set up their environment, they were using the default MPI library that's available on Cirrus, and this is this HPE MPT library, and they used that, and then they found that their scaling, their parallel efficiency was very poor once they went above 1 node. When they were using 4 GPU nodes, 16 GPUs, the scaling efficiency was less than 50%. So they came to us, they submitted a query to the help desk, and we could see the problem. We thought, well, we need to have more control over this MPI library that we have. We have the binaries for HPMPT, but not the source. But we could get the source code for OpenMPI. And then in addition, we can control, we can have quite a lot of control over the way the OpenMPI library is built on Cirrus. There are many configure options that we can specify to make sure that it's built specifically for the NVIDIA GPUs that we have and for the communications libraries that we have available, such as PMI2 and UCX and so on. And once we've done that, we could then build our central Python module such that MPI for Pi was linked to the OpenMPI library, and then asks the user to base their local Python environment on this new centrally installed module, which is what they did, and therefore their parallel efficiency improved a lot more when they're running across multiple GPU nodes. They got an efficiency of 80%, and the reason for that is because we can control, because we have OpenMPI, it does support direct GPU to GPU communications, and on Cirrus we have NVIDIA links or NV links that link the GPUs on a node. That's the 4 GPUs on the node, and then when you need to have direct GPU to GPU communications across nodes, we can go directly to the InfiniBand interconnect. So that kind of explains why we got the performance improvement we did with OpenMPI and not with HPE MPT. So also on Cirrus, we have a number of machine learning modules, and the way we set those up, we use something called Horovod. Horovod is a tool for running deep learning frameworks across multiple compute nodes, and Horovod has the advantage of being machine learning platform agnostic, meaning that I can use it with TensorFlow or PyTorch. I'm not restricted to a particular platform, and I thought that would be more attractive to users. So for each of the Python central modules, I also have centrally installed Horovod modules, which kind of extend the Python ones. And so for each of the 3 Horovod modules that are listed on this slide, you can see the underlying set of Python packages that are provided. So for the one on the right, say, the 0.26.1 version, I have the NVIDIA CUDA neural net library, as well as TensorFlow 2.11 and PyTorch 1.13.1. And then also, just to make it slightly convenient for users, I provide module aliases. So I would have a TensorFlow 2.11.0 hyphen GPU module, which actually is just the Horovod one. So, but if you wanted to run TensorFlow and you want to make things clear in your submission script, you can load a TensorFlow module or a PyTorch one if you prefer. So this is the way you might use Horovod to run a TensorFlow job across multiple GPU nodes. In this case, we're using 4. So we're using, I think we've got 16 MPI ranks, 1 per GPU. And so it's rather a complicated parallel job launching command. So we've got 3 parts to it, basically. I've color coded them to make it easier to read. And so you have the MPI run. So that's the job launcher provided by OpenMPI. And then you have various options there. So you're indicating that you're going to use Horovod. And then you have the bit where you're actually calling the Python interpreter. So you're calling that with your TensorFlow script. And then you're passing various arguments in green, which are the arguments that are interpreted by the benchmark script, which is doing, I think this one is just doing it's a ImageNet benchmark. So that's that. If you want to have further instructions on how to run Horovod using PyTorch or TensorFlow, you can refer to the link that's at the bottom of the slide. So to move into our second use case on Cirrus, what we have here is this one where we're extracting field boundaries from satellite images, and what's going on there is you're using satellite images of farmland, and then you want to have a neural network that can then work out where the field boundaries fall in that image, and it can automatically identify them rather than having to do this by eye, which would be quite time consuming. So this particular use case, it uses images that were taken by the Copernicus Satellite 2 satellites that orbit the Earth's poles. And in this example, I mean, previous work that had been done in that they found that they could take satellite images from, say, South Africa and use those images to train a neural network, and then go on to expose that neural network to images taken from Australia, and they would also find that that neural network could identify the field boundaries successfully for a different country to what the neural network was trained on. So in this case, it was quite useful that a lot of the centralized modules for the GPU nodes and for MPI were in place already, because there was quite a software stack that was required to put together. In particular, we needed something called a geospatial data abstraction library that would be able to work with the raw satellite images. And we needed various Python packages such as raster.io and also EOLearn and EOFlow. So these are things specifically for interpreting and getting satellite images into a form in which they can be fed into a neural network. And then there was a Git repo called field delineation, which were the scripts that the user was actually using. So that's just a summary of where we're at. So we have a local environment which the user had set up, and then this will be linked to the centrally installed modules, specifically the Horovod 0.26.1 GPU module. And so the user did this, and they were interested in particular in a region in Spain called Navarra, which is in the north of Spain. So just for context, up here would be Bilbao, the Bay of Biscay up here. This is based on the border of France. And so they took a segment of this region, and they have all the field boundaries there. So this is their reference field. And then they're interested in being able to take the raw images, those ones that don't have the boundaries indicated, and seeing if they could reproduce those. And basically see if they could train a network to reproduce those boundaries that are shown in the reference image. And that went quite well. The user, Dr. Simon Fravel, was able to run on one GPU using all 4 GPUs, and was able to train with a higher resolution data. So basically on their local cluster, they had the previous generation of NVIDIA GPUs, these Tesla K80s. So I think on Cirrus we have the V100s, slightly more recent, and they were able to improve their validation accuracy. So I think for 93% of that region, they were able to correctly identify where the field boundaries were. However, there were some issues with certain regions. So these are the sub-regions, if you like. They found that the model tended to under-segment the subdivisions of larger fields. But that worked quite well in that there was quite a lot of software to put together. So it was a good job that a lot of the central components were already in place, and we didn't have to worry about whether there'd be some incompatibility with the NVIDIA drivers / libraries. And Simon went on to do the same sort of work for many other regions across Europe, Africa, Southeast Asia. So that's Cirrus. I'm now going to go on to ARCHER2. ARCHER2 is our tier 1 machine. It is the national HPC resource for the United Kingdom. So that's a lot larger than Cirrus. It has just over 300, it has just over 750,000 cores, whereas Cirrus, I think about 11,000. And so this isn't an Intel machine, it's an AMD EPIC machine. We have a various amount of memory. The nodes are connected via the HPE Cray slingshot interconnect, and we have much more storage, around 15 petabytes compared to the 2 petabytes available on Cirrus. There are 2 research councils that fund the work on the construction and the use of ARCHER2, namely the Engineering Physical Sciences Research Council and the Natural Environment Research Council, EPCC and NERC. A lot of the codes used in ARCHER2 are from the materials science domain, so codes such as VASP, CP2K, and so on. There are also a few codes from the NERC domain, such as and NEMO. So on ARCHER2, things are set up a bit differently, and we have Lmod module files, and HPE Cray provide 3 programming environments: Cray, GNU, and AMD. That's the AOCC one. And each of these environments provides a particular compiler. And then they also provide a Cray Python module. So I'm hearing some sounds coming. I just want to check in case there's any questions being asked in the chat. Okay, so I'll come back to that at the end of the talk. I'll just go back to sharing that. So that one. Yeah, so HPE Cray also provide the Cray Python module, which contrasts to the situation on Cirrus, where we at EPCC built our own central Python modules, and the Cray Python one is built using the GCC compiler, and these are kind of some of the packages provided by that module, MPI for Py, for example, and NumPy and SciPy. And those packages, the MPI for Py one is linked to the Cray mpitch library, and I think NumPy and SciPy are linked to the Cray libsci module, and so that provides the various library routines to do linear algebra and so on. So again, the way you would set up a local Python environment on ARCHER2 is very similar. We try to keep it as similar as it is compared to Cirrus. You basically load your base Python environment that you want to extend from, and then you have the same commands, basically the Python-n VM to instantiate your local virtual environment, and then you source your activate script, and then you can then install your local packages as before. So it's exactly the same as it is on Cirrus. However, if you're extending from one of the Python machine learning modules that are available on ARCHER2, this is either TensorFlow or PyTorch, indicated in the top right, you do still need this extra command to do the extend VM activate. This just makes sure that your module environment is replicated every time you source the activate script. So in this situation, it is identical to the way it is on Cirrus. And again, if you're extending from one of the machine learning modules installed in ARCHER2, this is the kind of setup you would have. You'd basically have an environment that would bring together packages from 3 separate areas. Starting from the bottom, you would have the base Python module, this Cray Python 3.9.13.1. So you have your modules there, your packages there, such as MPI for Py. And then from the machine learning module, which is in the /work Y07 shared area, you have your PyTorch packages. And then in your local environment, which is under your user account, you'll have those packages that you need. And DGL is something called Deep Graph Library for machine learning. So again, as with Cirrus, if you need to do any further customization, you can add those in your activate script, which is held locally in the same way. And then running your local environment or running a Python script within your local environment over multiple compute nodes is very similar to the way it's done on Cirrus. I mean, on ARCHER2, it's just a quirk of ARCHER2 at the moment, you have an extra environment variable definition, So what we're doing here, just go back, is that you're just making sure that your Slurm environment variable is consistent with the srun equivalent. And again, there's a link here to the ARCHER2 docs that just goes over what I've explained in the previous slide. So a quick example of this use case, applying deep graph learning to molecular graphs. And this is about the idea that a molecule or an atomic system can be described by a graph, where the nodes in the graph refer to individual atoms and the links between them refer to the bonds. You can also have a very rich, it's kind of a rich description, such as you actually encode the details of a single atom, such as its spin and so on, the number of electrons. So this kind of thing can be converted into a neural network. And then you could, if you wanted, then use that neural network to identify similar molecules. Or you could go further than that. The DGL library actually has a pre-processed version of a dataset containing the details of 40,000 drug compounds, and you can sort of have a binary classification has been applied to these compounds that indicates whether or not a compound will inhibit a particular virus. So you can train a network on this, and then you can introduce new compounds, and then the network can make a prediction as to whether or not it would inhibit a particular virus. And then if it does, you obviously you would like test that out in a lab. So here's a particular example, just showing you how easy it is to set things up to use the deep graph library. You would, when you're on the login node on ARCHER2, you would load the appropriate centrally stored module, which is PyTorch in this case. You then go through the same steps as you do on Cirrus, which is in Cray. Won't go over that again. Then once you've activated your activate script for the local environment, you're then ready to install the specific packages that you need. So that's obviously deep graph library, DGL Go, which is a command line tool, and then some other packages, PyMatGen, which is a Python materials genomics, and that's an open source Python library for materials analysis. That's just helping you to read in the input data, and then something called Torch Geometric, which is built upon PyTorch and allows you to more easily use graph neural networks. So this will be the Slurm script that you might have to submit your job. It's a little bit confusing here. I'll try to color code it. So you've got something called DeePM. The D doesn't stand for deep. This is an MPitch term, so this is for relating to MPI. DeePM just stands for Dynamic Process Management. This is something we need to set in order to prevent MPitch from complaining. And then DGL, that does refer to Deep Graph Library, and you're specifying the machine learning backend to that. And then here you're specifying the number of workers you want. And then you actually launch the Python job here, and we're using the MPI for Pi futures module, and then we're passing in the actual local Python script called grapher.py. So I explain a bit more. So inside that the script grapher.py, this is what we're doing. We're importing an object from the futures module called MPI pool executor, and that's being set up down here. And that's going to be, so that's going to manage a task farm, and the workers are going to be calling this generate function. And what that does is it basically converts a crystallographic information format file into a Python module file. And it's using DGL to do that. It's using various packages such as PyMatGen, DGL, and Torch, and so on. So those PyTorch modules could then be used to identify molecules, or they could be used as input to do further machine learning. And a user did this, and we were able to, so this is just explaining that the MPI pool executor is basically just a task farm. And we're able to, we are limited, unfortunately, to running on one node, but you can run multiple single node jobs within a larger job submission. And so with this, you can run about 20 nodes. Each of them is managing a separate task farm, but you can then convert about 50,000 CIF files to PyTorch model files in about 40 minutes. I guess how long it takes will actually depend on the individual CIF file. You can do the same thing, but instead of using MPI pool executor, MPI com executor, you can use that instead. The syntax is a bit different down here. A second use case, now we're going to use machine learning to do a molecular dynamics simulation. This is using something called a DeePMD kit. So this addresses a problem known as the accuracy versus efficiency dilemma in molecular simulations. This is when you're interested in potential energy surfaces or in interatomic forces. So you can run an empirical force field model, and you can then run large models that contains many atoms, and you can run them for long times, and that's perfectly okay. Although the accuracy is questionable, you might want to use more accurate algorithms such as density functional theory, but then you have a problem with when you use larger models, it quickly becomes too expensive, computationally speaking. And so the purpose of tools like DeePMD kit is it allows you to achieve a high level of accuracy, but still you can use machine learning to mitigate the computational expense. So it kind of the expense grows linearly as you increase the model set, the model size, for example. And so in this case, we were using LAMMPS. So the user needed to set up a local environment that would have DeePMD kit in it, but also a LAMMPS installation. So this is where things were installed. It's a little more complicated than the other use cases. Within this folder are 3 subfolders. We have DeePMD, which contains the actual local Python environment. But then we had something called DeePMD kit, which is where we had our C++ interface. And then we had the actual LAMMPS source code and installation. So the idea is that we'll build LAMMPS, and then when we submit a LAMMPS job, it will actually, instead of just doing a traditional time stepping through a molecular dynamics simulation, it will then call a library provided by DeePMD kit, which will then be passing the current state of the simulation to a neural network, and then that will make a prediction as to what the next step will be, or what the next state will be, and then so on. Then that will be fed back round, and in this way you step through the simulation. So this is the way things were installed. So for the Python interface, it's quite straightforward. I think you just cloned a GitHub repo, and then you went into the repo folder, and then you run this pip install dot command. When you're building the C++ interface, it's slightly more involved. You have to use CMake, and then you have to indicate where the LAMMPS source code is located, which is the purpose of this LAMMPS source root environment variable here. And then you also need to build your local LAMMPS code, which is just the same as it would be done otherwise, just indicating where the fast Fourier transform libraries will be on ARCHER2. And then you're ready to run your job. And you can see the way it's done. You run LAMMPS as you would do normally, as if you weren't using machine learning. But there's something extra. I mean, the input file you're passing in has a crucial detail to show you what that contains. So that contains this path, which points to the library provided by DeePMD kit, and this is the one that will do will instead use the neural network in order to predict what the next step would be. And so the user is able to do this, and for a fairly small system, a 300 atom system, that they could do about 90,000 steps per hour. So that equates to about 1,000 picoseconds of simulation time. An important thing, they found that their results were the same as when they ran on their local cluster, but using an older version of TensorFlow. So that's those examples. There are quite a few other examples, which I just referred to briefly here, both for Cirrus and ARCHER2. when I mentioned to James back at the beginning of May that I wanted to give this talk, I was kind of hoping that some of the users that I was helping would need to run their jobs over multiple nodes. That proved not to be the case. So I'm still interested in helping users to do that, to see how that works. I have run ImageNet benchmark, an image recognition benchmark using TensorFlow, and achieved reasonable performance across multiple GPU nodes. And then there's I found recently something else to watch out for is a side effect of installing the newer versions of TensorFlow and PyTorch and ARCHER2, is that they do provide newer versions of NumPy and SciPy, newer compared to the ones provided by the HPE Cray Python module. And so that may have an impact on performance because those particular versions, 1.6.2, 1.2 and 1.5 have been built against the particular Cray ellipse library. I just put it here to remind myself to talk to Cray HPE about this. So just below are the links again to the Python pages on the Cirrus and ARCHER2 docs. So thanks for listening. With that, I'll stop the presentation. I don't know if there are any questions.
Well, thank you very much for a very lovely talk. There's one question in the chat around OpenMPI versus MPitch on ARCHER2.
Okay.
I don't know if you can
I'll just see if I can see that. Is that the one that starts with developed our own? Oh yeah, we've developed our own on ARCHER2. I thought it was. Okay, so yeah, so that's better. So on Cirrus, OpenMPI is available and has been built specifically for the hardware. On ARCHER2, there is an OpenMPI library available, but that is a bit more experimental. So I believe that if you had set up your own Python environment to link to that, I mean, the OpenMPI library is held as a module, but in the development area on ARCHER2. So you would have to run a particular module use command to access it. So you would need to, if you wanted to use that, you would need to actually build MPI for Pi within your local Python environment, build it from source such that it is linked against the OpenMPI library. That's also on ARCHER2, albeit in the development area. So you might, Lang, you'd have to, if you could raise a query on the help desk, we'd be able to help you with that. Yeah, that's fine, no problem. So from Jack, can you comment? Okay.
So just to, so I'll just read it out to the people watching this recording. So can you comment on the network connection that the results from Python import modules, pip install packages, virtual environments are stored on the network file system. When run in parallel, all ranks of the MPI job need to touch all of the imported Python libraries, calling long startup times for code run in Python.
Okay.
Are there tools available to mitigate this?
No, we haven't really encountered this yet with users, but I understand it is a problem. So we'll be looking at this shortly. I think especially as people want to run multiple nodes, and they will be using more MPI ranks, so they will start to hit this issue. So sorry, don't have anything as yet, but we'll be starting to look at this soon.
Okay, as we don't seem to have any more questions, I think we will bring the session to a close there. Thank you for everyone attending this week. Our next webinar is in 2 weeks' time, I believe, on looking at integration between LAMMPS and OpenFOAM, for those who are interested in that. Otherwise, keep an eye out on the ARCHER2 website and the newsletter that's sent out weekly by Claire for more announcements about sessions like this. Thank you again for giving a lovely talk, Michael, and speak to you soon.
No worries. Thank you. Bye.